Okay. By the way, Vlad, do you usually copy the recordings to YouTube or you keep it in a drive folder?
Yeah, I upload them to YouTube and then just share that link on the website.
Okay. Because I just noticed that the notification says that the recordings are kept in the drive folder only for 3 months. So
Wow,
they would
that's good then.
disappear.
We won't lose them.
Yeah, that's good. Okay. You don't see my screen. That's weird. All right. Okay, now you see it. Okay, functional approximation. Here we go. I thought that we're going to do some time travel. I just gave a talk, and so I'm recycling some of the slides from that talk. And I think it's kind of a neat introduction to functional approximation to do this time travel trips. So the year is 1963. I think man goes to moon and like, I don't know, Beatles and whatnot. Lots of things happening. And among those things is this paper by Richard Palmon, Robert Calaba, and Bella Kotkin. And as probably many of you know, kind of Palmon is attributed as the father of dynamic programming or whatever, right? He was definitely highly influential in promoting these ideas, and then was a very prolific writer, wrote many books about this topic, um, and was in general very invested in making these things work. And so there is this paper from 1963 where he is still trying, and I think it's a very interesting paper. Its title is not as catchy as a Nurip's title would be these days. You could say it's pretty boring. Polynomials are mentioned, and okay, dynamic programming. That's fine. Nurip standards wise as well. And allocation processes. What the heck is that? I guess you would never read this paper unless I presented it today for you. So let's look at what this paper is about. So first of all, the problem that these people were studying is a very simple computational problem, if you wish. They call it the allocation problem. And for some reason, they were obsessed with this problem. I guess they probably had their reasons. You can, I don't know, come up with practical examples where this is interesting, but it has an interesting structure anyways. So what is this problem? You have some money. Let's call this amount B, right? And you want to divide it up because you have 8 children or something. Okay, so you divide up the money into 8 parts. Okay, maybe projects, not children. Like you're gonna like spend some money on each of the projects, and for each project you can expect some revenue, and this revenue is some. It's hard to see, but there are these curves on the slide. So some nonlinear function of the investment in every project, like that's the payoff that you get, right? So it's like, where is my pen? Pen. Oh, it's here. A white pen on the white notebook. So there was this function, there's this function. So generally, like you can allocate money from 0 to B in a project. And if you're allocating the money into that project, then maybe someone tells you that, well, okay, the more you allocate, the better you are off. So this is your revenue. This is the money allocated. The more you allocate, the better you are. So this function is increasing. And for the ICE project, this is how the function looks like. Maybe it could be a simpler function as well, but some function that is given to you. And then someone asks you like, okay, how do you divide the money between these different projects? Well, you want to divide it in such a way that you're maximizing the total revenue. So from each of the projects, if you're allocating AI to it, you get GI-AI, and you sum up all the money, and you have to maximize this by creating a proper allocation of the funds, which means that, well, you can't spend more than what you have, and there is no shorting, so you can't spend negative on a project. You can spend zero. And so this is what's called the allocation problem. And you can imagine, I don't know, the multidimensional version of it. It's going to be interesting when you have different types of resources and then you want different splits. So in this case, AI would not be real, but it would be in the positive quadrant of a p-dimensional space when you have p different things, and then b is a p-dimensional positive valued vector. That's the multi-dimensional allocation problem. But otherwise, it's the same problem. And then the question is, okay, like what are these, like how do you allocate? And so Baemon's idea probably was that you should view this as a multi-stage process, where at stage H, you're deciding about how much you're allocating to project H. And if you do it this way, then you can define this optimal value function. You can view this as a kind of like a control problem, right? Where you have how much you have spent so far at stage H. So that's summarized with your state S. So that determines how much you can spend in the rest. So that will be B minus H, B minus S. That's how much you can spend in the rest. And now for the current stage, which is H, you have to decide about how much you want to spend in this stage. And the remaining is going to be spent on the further stages. And you can define the optimal value to go for this subproblem. So it's in a way, it's dividing up the big problem into these subproblems and then solving them one by one. And the optimal value function gives you this summary. And okay, if you write the optimality equations for this problem, then to simplify things, you can define as a boundary condition the optimal value function for stage H plus 1, when you can't really make any money. It's identically 0. And then you can just write the optimal values for every stage. And if you think about it a little bit, it has to satisfy this equation, which is today called Biomass optimality equation, which just says that, well, you have to decide about how much money you are allocating in the current state. It has to be between 0 and B minus S. S is how much you spent before. And then you get the proceedings for the current stage. So that's GH of A. And you get the optimal proceedings for all the next stage. So to act optimally at stage H, you only have to know how the summary of how you would be acting optimally from stage H plus 1. You don't need to know the details. You just need to know how much value you would get. The value function actually gives you that. So you have this optimal equation. And so they realized that you can write these equations. The problem is that S is a continuous value between 0 and B. So you have these functional equations, and then now you have to solve these functional equations. How do you solve this? Wow. Okay, this is just like showing it with pictures, but it's the same thing, and it's also explaining that, well, if you solve this, then you can get the optimal way to act by looking at the action that gives you the maximum value in the Biomass optimality equation. So that's a greedy one-step look ahead. And so how would you solve this? Well, you would solve it by the simplest thing that comes to mind, by discretizing and then somehow doing linear interpolation, right? So, so here when you have to do the calculation for stage H, you have a state. And for that particular state, you need to consider all actions in this interval, like where you can step. So it's like the 0 is put here, then this is b minus s. So in this interval, you have to consider all the actions. And then if you already have this other function, then you can read out how much you would get. You add to that how much you get with the um, current reward function, if you wish, and you solve this maximization problem, then you get a value at that point. But you have continuously many points. Well, what can you do? Like, you could try to discretize this range, calculate these values at these discrete points. And if when it comes to do the calculation for stage h minus 1, you need the whole function, not only the discrete points, or going back to h plus 1. You only have these discrete points, but okay, if you need some value in between because of this maximization, like it would consider all possible values in this range. So you need to know how the value function behaves here. You can do linear interpolation or whatnot for the values in between. Okay, so that would be a simple discretization-based approach to scaling up things so that you're not limited by to discrete problems where the number of states is finite. Number of states were continuous. Did it matter? It doesn't really matter. You can do this discretization, and you can imagine this works pretty well. For example, if you have an allocation problem, which is one-dimensional, which is that all of these resources are like one type of resource, just money. Okay, but what happens if you have a p-dimensional problem? So p is the different types of resources that you need to all split up. Then if you try the trivial thing, just to discretize this cube of p dimensions at some granularity of epsilon, then you get that there are this many points in your grid. B over epsilon to the power of p. And if p is growing, it's getting large, then this grows really, really fast. And it very quickly grows larger than what you can store on your computer, especially in 1963. But even today, this is exponential growth in p. It's really bad. So you can't really hope to solve, I don't know, 100-dimensional problems this way. You would need to choose, like even if you choose epsilon to be b over half, like you have like one midpoint, then you get 2 to the 100 in 100-dimensional space. And that's like, oh, it's a big number. You can't store that many reals on your computer. So this discretization approach very quickly runs into a wall. Nevertheless, this was heavily investigated by Bauman and colleagues. It was the state of the art until this paper came along. So they were first considering this discretization and like very low dimensional problems. Anyway, so Bauman calls this a curse of dimensionality. So he's this scary figure reminding us that this is really bad. Don't try to discretize high-dimensional problems. Bad things are going to happen. So the new idea in 1963 was to get away from discretization So how do we get away from discretization? I don't know what happened to my slides. These were supposed to be nicer. You will soon see once slide updates that. Uh, okay. Anyway, so this was not supposed to run into each other. So we can just come up with some basis functions and then take the linear combination of these basis functions. So if you're in one dimension, then I don't know, Legend functions or Chebyshev polynomials would come to mind. And how do we, so there the point is that even if you're in higher dimensions, then maybe you can find some basis functions such that only a few basis functions are necessary to represent your optimal value function in a quite precise manner or even exactly. And the number of coefficients is kept independent. So this is D. So D can be kept or scaled independently of the dimensionality of the domain. Like nothing tells you that D has to be, 2 to the P. It doesn't have to be 2 to the P. It can be much lower, right? So you're decoupling the dimensionality of the input space from the way the value functions are represented by considering a more general approach, which is based on this view that functions should be represented as linear combinations of other functions, the basis functions. Of course, discretization is a special case of this. But here, the point is that you can do this with other basis functions. And if you are in a multidimensional domain, then maybe you're not going to be the slave of the dimension anymore if you do this. You definitely will not be a slave. You're decoupling. You're saving yourself by doing this. Then the next question is, how do we get the coefficients? And you could, I don't know, like set up some whatever methods. One possibility is that these people are investigating is that if you have basis functions which are orthonormal, then the best coefficients in terms of the quadratic error are actually obtained by just calculating the correlation of the function and the basis function. So the Ks coefficient is just this correlation. It's just because of the way things are set up. So that's a simple calculus result. And so that means that if we want to have the coefficients, we should be able to calculate these integrals, maybe in high dimensional spaces. How do you calculate integrals? Well, Monte Carlo propaganda, right? So you could use sampling, or you can use Gaussian quadratures or whatever. Like you use your favorite integration technique that supports you best. And this paper was looking at Gaussian quadratures. So in Gaussian quadratures, the idea is that the integral is calculated by evaluating the function at a fixed set of points. These are like nodes in the space, Si, and there are R of them. And then take the weighted linear combination of this, where the weights are set up in such a way that if you're integrating functions which are nice, like they are of the same type as your basis functions, then you get the exact integral value. And so if you do this with polynomials, then this is Gaussian quadratures. And so that means that like if phi is a polynomial and f is a polynomial, then you get the exact result. Of course, in our case, it's a lie because f is not going to be a polynomial, but okay, maybe it can be well represented by a polynomial of a low degree. So that's what we are betting on. So then what's the loss? Like there is no loss, right? So it makes a lot of sense to try to use a method which is tailored to this very special case because we are anyways betting on that the optimal value function is going to be a low order polynomial essentially, right? So this makes a lot of sense. Like these people were pretty clever. So then you can put together everything. You have these knots, and you have the weights, and you can initialize your procedure because VH plus 1 is identical to 0, and that stage age, then you have to do this calculation. I don't know what happened to my slide. I just copied these slides from one presentation to another, and like it's not completely gibberish now, but it's a little bit questionable the quality. Anyways, it's still readable. So then the procedure would do two things. So first, at the knot, just do the calculation as it was doing it before. So that's like the discretization procedure was already doing this. So considering all the actions, solving the maximum, and this V fun. Okay, so this is, I don't know. I will try to just run with this slides. So here, what you don't see is that this is just like V fun. This is like a Python code. So you write this function, it takes two inputs, the state and the parameter vector, and it just like returns the value of the sum of the correlation between parameters and the basis function evaluated at this point. Right? Just like what the function approximator is doing. And so that uses the previously calculated parameter vector. You do this for all the actions. You take the maximum. So that's what this blue triangle is doing. And then you get a value, and then you can do get this value at all these knots. And then in the next step, you can do the interpolation. And the way you do the interpolation is that you just get the parameter vectors. And then here you use the Gaussian Quadratures formula, which was saying that, well, the coefficients, which are the correlation between the function of interest, the optimal value function, and the basis function can be evaluated by taking this weighted linear combination of the function values at the nodes correlated with the basis function value at the nodes. And so that's the whole calculation. Okay. And so this is the procedure that they propose essentially in this paper. And so this way you are extending it to the whole range. You have the parameter vectors. So now for any state of interest, you can ask what's the value, and this vfun function can give you the value, right? Given this parameter vector. So that's like the compressed representation for the optimal value function. So what we're doing is that we do some pre-calculation and then create a compressed representation for the value function. And then we go stage by stage from the last stage to the very first stage. That's it. And it's very similar to the discretization approach, but it's radically different as well, because we are not confined to this very particular way of doing interpolation using discretization. So you can do interpolation in many ways. Okay. So this procedure today would be called an instance of fitted value iteration. Of course, these people didn't call it like that. And there are many other variations. You can do this with neural networks, with least squares fitting, Monte Carlo, you name it. In an exercise, you will analyze the linear version of it. And so now we know a lot about this. And coincidentally, it was also, it's also basically the procedure that is um, in this paper by my DeepMind colleagues, where they were applying reinforcement learning techniques to learn to play Atari 2600 video games. And they were able to demonstrate that they can just run a single algorithm, DQ1, which is in a sense a version of fitted value iteration. Okay, with neural networks and whatnot, and that was pretty important that it was using neural networks. So, well, Okay, there is a follow-up paper that says that maybe it wasn't super important. So you can, if you bump into Marlos, he's also somewhere here in Edmonton, he can tell you about those experiments where they were trying to reproduce the results of this original paper with linear function approximation. And they were mostly successful, I would say. But it was a bit of work anyway. So it's the same algorithm, and it's used all over the place. And we can trace it back to this paper in 1963. So, okay, what's the gain by changing this view? I, okay, yeah, I plugged my mic out. So I think you can hear me fine now, right? Okay. So what was the gain? Well, we decoupled the dimension and the needs of the algorithm from each other. So even for high dimensional problems, you can choose a low order polynomial representation regardless of the dimension. That's it. There is no magic in there. It may be a bad approximation. It may not work. So you need to rely on your luck to be able to come up with good basis functions or good neural network architectures or whatnot. But it seems to work. And okay, so we're not the slave of dimension anymore. So there is no P. So we can choose D and R the way we wish. We can choose it whatever number we can deal with, like scale it to the actual computation resources that we have. All right, so there is no curse in the sense that we are not forced to blow up with the dimension if we do this. It's a very simple thing, right? Okay, so we can run this procedure. It's good. So why is this relevant? Well, it's like, okay, this equation is pretty much the same as the Bellman optimality equation we would get anyways with our Markov decision processes. And you can run the same thing in a Markov decision process as well. You would just need to modify in very simple ways how these backups are calculated, and there you can use a simulator if you have access to a simulator, right? Like it's just like you have the nodes and then you go into the nodes. In the nodes, you would simulate maybe multiple transitions for every action that you have. Calculate this sample mean instead of the true average, but the sample mean should be a good approximation to the average anyways. And so the procedure can be straightforwardly generalized to Markov decision process, and that's the algorithm that people are talking about a lot. And okay, so this, right. So the area hypothesis is that dynamic programming and functional approximation is the key technique to solve large-scale control problems, or more precisely MDPs, is kind of like the central theme of reinforcement learning, if you wish, or should be. If you ask me, this is the central hypothesis, and for a large portion of the class, in the remaining class, we are looking at to what degree this hypothesis is supported. Like, is this true? Like, can we do this or not? And so we do this theoretically, but a lot of people are running empirical tests. And so here you see the IBM 7090 supercomputer of the 1963s, and some other people, these are not the authors, but like just some picture from the internet. So the paper actually says like it's reproducibility, right? Like they say we ran these experiments on this supercomputer. We wrote the code in Fortran, and it took us seconds to minutes to calculate the results on this supercomputer. And I read that this was really, really expensive to, I think you had to rent it and pay for using it. There were not many powerful computers like this. And this computer was, I think it was like 10,000 times less powerful than the Atari 2600 video console. And today's computers are like a billion or 100 billion times more powerful than this was, which is like, wow, okay, big numbers. Anyways, they ran experiments, believe it or not, and they were really optimistic about the results. Like they were able to solve 2, 3-dimensional, sometimes 10-dimensional allocation problems. And they were very, very optimistic. So they wrote at the end of the paper, this is a big conclusion. If you combine these techniques, polynomial approximations, they were aware that like you don't have to use polynomials, like but general basis functions. Well, that's what I mean. Lagrange multipliers. So where is the Lagrange multipliers? Well, they have to solve the maximization problem, which is a constraint maximization problem. So it's like, that's the Lagrange multipliers. Instead of successive approximation, that's function approximation. There should be very few allocation processes which will resist our efforts. Very heartwarming message. And here we are today. People are running the same algorithm and solving, okay, not only allocation processes, but some really big problems to a surprising accuracy and fidelity, if you wish. So it's quite interesting. So, but okay, if you're in theory, then you ask the questions. But does it work? Does it really work? Like, well, it's good to have these empirical results. It's very reassuring. Without the empirical results, there would be no reason to look at the theory, right? Like if you don't have good empirical evidence, then like what do you care about showing that something doesn't work or something works or whatever, right? Like figuring out the truth is only interesting if that truth could be used. Anyway, so there are two questions that you could ask. That is the question of what degree to use and what basis functions to use for a particular problem. So here we go, allocation processes. The G functions, like that's all that you have. You start with that, and then it's your turn to propose some basis functions. What basis functions are going to propose? And can we trust that these basis functions are going to be good enough, and a few of them is going to be good enough to capture highly accurately the optimal value function, because this whole program relies on the success of this. So this is the question in the realm of approximation theory, systems theory, because you have the systems and then you are asking about the smoothness of the value function. Like, can I choose some basis such that the value function can be represented with just a few basis functions? This is a smoothness approximation theory question, and also systems theory question, because the value function is implicitly defined in terms of the dynamics and the rewards. It's not explicitly given to us. It's an interesting set of questions, but a set of questions that is not the one that the computer scientist would ask. Computer scientists would ask the question regarding the computation, but okay, like assume that someone else did the job and chose the basis functions. Can we even compute this thing? Can we do the computation in an efficient manner? Is it really true that like once you solve the approximation problem, like the systems people are very clever, maybe figuring out these basis functions, but it would worth nothing if you cannot write a code that scales in a favorable fashion with the size of the problem, because then we won't be able to solve big problems. Okay, so why is this really a question? The reason this is a question is because the optimal value function is not given to you in an explicit form. It's encoded in the dynamics of the system, right? And encoded in the reward. It's not like that you can just read out the value of the optimal value function. You can't just read out the value of the optimal value function. If you try to do that, you would need to do something like the look-ahead calculation that we were doing. And we saw that that blows up exponentially in the worst case without any assumptions in the horizon. So if the horizon is big, there is like there is no like without using the extra information that there are the features, there is no way you can get these optimal values. Okay, so you need to use in the calculation of the optimal values this structure that the optimal values can be written as linear combination of these basis functions. If an algorithm is not using this, then it won't be successful. Okay, so but then it's like a circular problem, right? Like um, the snake biting its own tail. We would need the optimal value function, the device of the optimal value function to actually do the calculation. Well, if you have the finite horizon problem, you're calculating backwards, then you can try to do this backwards calculation. And you were only relying on things that were done at later stages, and then fitted value iteration, it seems to be like a bona fide procedure that could even work. It is still a question whether the errors are going to blow up or not, because you're going to have approximation errors, representation errors, estimation errors that come from, randomly sampling stuff and not having the access to the true values. And maybe, like they're going to, have multiplicative effects in terms of the errors blowing up. And then that would mean that if you have a long horizon problem, then you still end up with calculation that is maybe exponentially costly in the horizon. So it's absolutely non-trivial. So this is the question that we're after in this class. And this is the exciting question, I think. The other question is also exciting, but it's exciting for other folks, I guess. Someone need to look at the approximation theory questions as well. Well, sometimes we do too. Anyway, so that were the slides that I borrowed, and that replaces everything that I said last year. Because I think it's good to see these examples where people are actually trying to do something and specific examples. Anyway, so the last time I told you to maybe look at this presentation by Kenneth Judd, of course, of Dimensionality, where is thy thing, and where is thy thing, and here is the reference. It was copied to Slack as well. And so today I'm going to a particular slide in this presentation because Jude is also talking about how to choose these basis functions and like this function approximation methods. So it is a slide that is from this presentation. So he's making some points, and I wanted us to think about these points. And here there are some specific references. So the specific reference he mentioned is this paper. And here are two links. This is like a draft, and then this is the final paper. With the university account, you can download the final paper as well. It's nicer than the draft. Okay, so what does this slide say? So it says basically one thing: don't use tensor product approaches. Okay, so what is a tensor product approach? The tensor product is similar to the discretization idea. The idea is that you have basis functions for each variable. So there are variables x, y, z, and like you have p of them. We don't have that many letters, so we just stop at z. And for each of them, you have basis functions which are just dependent on that variable. So you could have the polynomials, for example, the xi's and the yj's and the z to the k's. And then you consider all products of these one, like basis functions that are defined only for one dimension, one variable. And you consider all possible products up to degree m. So this would be the tensor product construction. So the general form of this, of course, would be something like I think that there is a k here missing. AI, j, k, and phi I, x, and then multiplied with phi j of y and phi k of z. And you can imagine like how this goes with p dimensions. And then the point he's making is that in this tensor product constructions, people tend to just assume that I, j, and k are chosen independently of each other between values 0 and m. So there is going to be m cubed terms, and in p dimensions, you're going to have m to the p terms. So that then what are we doing? It's like we said that one m is 2 and p is 100, then you have 2 to 100 terms again. So that's not better than discretization. And actually, somewhat ironically, in the paper of 1963, this tensor product construction comes up. So it's like they say that, well, in higher dimensions, you can use tensor product. So Jude says, okay, be careful with that. Because you can run into the same problem that we were facing before. So maybe don't do this. And then he's saying something really interesting. He says that the degree, the proper notion of degree in multivariate context is the sum of the pairs. So do you know why this is the case? Like why we should call the degree of this multidimensional polynomial the sum of the pairs? Do we have some intuitive notion about like what this degree should be?
And if they're all the same thing, then the degree would be the sum of them, clearly.
Yeah, that's a very, very good point. I would have started with that. So if x equals y equals z, so you're basically along the diagonal, okay, in 2 dimensions. You're going along the diagonal, this diagonal. Then, of course, x to the power of I, y to the power of j, z to the power of k can be rewritten as x to the power of I plus j plus k. So this is what happens along the diagonal, right? And so you see that along the diagonal, you have a polynomial of this degree. And so if you never had any intention of using polynomials of higher order than m, then that means that in this sum, you should confine yourself to I, j, and k such that their sum is less than or equal to m, or you're going to overgenerate along the diagonal or along these lines, okay? So more general way of thinking about this is that if you had your domain and you take whatever line in this domain, so that was this multidimensional domain, and now you are on a one dimension, or you take array. So you are in a one-dimensional case. You're back to the one-dimensional case. And if you want to have just a low degree polynomial approximation along any line, then you never need the degrees bigger than, the degree then like should follow this definition, and you never need the other coefficients. This is sufficient. And you don't want to overgenerate. It superfluous to overgenerate. It creates kind of like an unnecessary high degree of approximations along special lines. So it's kind of like a non-uniform approximation and favoring diagonals in some weird way, which is usually not the intention. Okay. So I saw that this is often neglected, overlooked, and yet it explains, I think, a lot about why can we get away with functional approximation in high dimensional settings with relatively low degree polynomials or relatively few coefficients. The number of coefficients doesn't have to scale like this. Okay. All right, so that's a little inlet about tensor products and why not use them. And even in my book that I wrote about RL, this little book, I mentioned tensor products and I didn't mention this. So definitely have to add something to that. So, okay, I hope this is pretty clear. So the next point is to look at this jungle of assumptions that you can have. So we're playing this game when we're going to make some assumption about the MDP. So we're not considering any MDPs. We're considering MDPs together with feature maps. Somehow the algorithm is going to have access to a feature map. And we only consider the MDPs which are playing nice with the feature map. But playing nice with the feature map can be defined in zillions of different ways. Okay, so the one of the simplest way is to say that, well, okay, so you have your function class. These are the functions that you can compactly represent your function approximator. So if you are in the linear case, then these are all of these functions that S is mapped to some of theta I of phi I of S, and theta 1, theta D is just reals. So this linear space, it's like you have the RS, that's a huge space, and this is just like a linear subspace of dimension D. It's like a very, very small subset. It's a very thin subset of the big S-dimensional fat space. And so the very first assumption that came up comes from the 1963 paper, is the assumption that V star lies in this function space, and then ask the question, okay, can we do some calculations? Can we perform these calculations if this happens to be the case? A similar assumption would be that Q star lies in the associated other function space. The other function space is F prime, which maps to every state action pair. So know your features are for state action pairs. And otherwise, it's the same thing. So this is a d-dimensional subspace of this even bigger space, which is R to the SA. So the second assumption is that Q star lies in this functions, set of functions. Can you do the computation in that case? Other assumptions, so slightly more confining, more restrictive, are slightly or not, I don't know, like it's just more restrictive assumptions that sometimes you see in the literature. Could be that the value functions of any policy that you can think about, or like all the policies that are deterministic or stochastic memorized policies, the value functions of all those lie in the function space, so they can be represented exactly. Or the action value functions lie in the associated function space. So obviously these are less general than this, right? So they rule out more MDPs, because if this holds, like let's say the first holds, then sorry, if this holds, then definitely the first holds, right? So if for any policy V pi is in F, then V star is in F because there is a policy that realizes V star. So the optimal policy's value function is also representable. So the first condition is more general, so less restrictive than this third. In general, these V star Q star things are incomparable, except that if you have deterministic dynamics. So if you have deterministic dynamics, then for finite horizon problems, then if you have Q star realizability, then you can define a new MVP such that in the new MVP, you derive the features from the features you had for Q star realizability. And the new MVP will have features for states. So you have a new state space. And you can guess that state space is going to be pairs of states and actions. And you just like use the features associated to that, and V star realizability is going to hold there. So there is a reduction like that. So in a way, then that shows that V star realizability is for these problems is more fundamental than Q star realizability. In general, we don't know these relations. Okay, so the next bunch is talking about, still you have policies, and it's talking about that if you apply the Bamon operator underlying the policy evaluation operator underlying a policy, and you were in the function space, then you stay in the function space. So that's a closeness assumption. Okay, you can do this both with state operators acting on a state or acting on state action value functions or state action functions. Another related closeness is just requiring this with respect to the Bamon optimality operator. So these operators in particular are linear operators, and this is a nonlinear operator. So that's a very different assumption. And you can guess that, well, value iteration kind of like just iterates through T. So if you have a closeness assumption like this, like the latter one, that would be a very good fit for value iteration. Policy iteration, on the other hand, uses the policy evaluation operator under the hood because it calculates fixed points of that. So the previous assumption is a good friend with policy iteration type of algorithms, right? So this is PI friendly. This is VI friendly. Okay, and then there are also two other assumptions that come up, which are even more demanding, so even more restrictive than the previous ones. So there is this assumption here, which you could say, so this is the low rank assumption. This just says that if you take any function of the states and you apply the corresponding policy evaluation operator, no matter the policy, then you're being mapped. The result of that is going to be in your function space. It's linearly representable. So that's kind of a low rank assumption about the transition kernel. So in the literature, sometimes this is called the linear MDP assumption. Sometimes this is called a low rank kernel assumption. And there are variations of like whether you include the reward function or you just apply this to the kernel operator. So you can replace T with P of pi. P of pi is the Markov kernel, which is viewed as an operator mapping functions to functions.
So
yeah.
I was going to say, are there any other nuanced differences between linear MDP and a low rank kernel, or would you say they're like in their definitions?
So there are multiple definitions for low rank kernels. So the literature is really confusing, and so it's not really worthwhile to spend a lot of time on that. You just have to be very clear if you are using any of this, just like give the definition, call it whatever you want to call it. It's not standardized in a proper way yet in the literature. So when people say linear MDP or low rank transition kernel, that could mean multiple things. So you always have to ask, unfortunately. Yeah. Anyway, so there are relatives to this. that correspond to the Bamon optimality operator. People are not really into that because then there are these weaker assumptions, these closeness assumptions, and then they're always like there is no juice that you can get. Well, okay, you can get some juice from this too. In some settings. So in some settings, it's much better to have these assumptions. So in the online setting, for reasons that will become clear at the very end of the class, somehow in the online setting, you want to, you're in your function space, and then somehow you leave your function space and you want to get back, desperately get back, because you need compressed representations. Then magically, you just assume this, any of these, and then you're going to be fine. If you try to run with this, then you're still in trouble and you have to work much harder. And maybe the result is true, or maybe there is a procedure that does everything you wanted. Maybe there is none. Maybe no one knows. So it's like there are delicate differences between these different assumptions. And so here I'm pretending as if we would really mean that, let's say, going back to the very first assumption, that V star belongs to your function space. But yeah, like that would be too much to assume. So generally, you just want to assume that it lies close in some norm, usually L infinity norm. So it's misspecified setting, and the misspecification error is measured in this norm. And then you want algorithms that whose performance degrades in a graceful manner as the level of misspecification increases. By which we mean is that like a small misspecification shouldn't completely throw off the algorithm. And there are algorithms which are completely thrown off by a really tiny little bit amount of misspecification, which are very sensitive. So these are the interesting questions to ask about these algorithms. Are they sensitive to this misspecification or not? To what degree are they sensitive? We also know by now, and we're going to learn about this, that there are differences between algorithms that were proposed in the literature in terms of how sensitive they are to this level of misspecification. Some algorithms are less sensitive than others, probably, which is quite interesting. All right, so this is my little intro about these modeling assumptions. And now we can go to the questions from Slack. Matthew, are you around?
Hey, yeah, I'm around.
Good. Can you ask your question?
Sure, definitely. So actually what we talked about today was kind of useful and kind of addressing my question a little bit. But with the discussion of different basis functions in the lecture 7 notes, I was just kind of curious because I do some of my research is in functional data analysis. I'm coming from statistics. I was wondering about common choices of bases, if there are any. Perhaps it's more interesting to discuss continuous state spaces rather than discrete, though.
Yeah, I mean, I don't have too much to add to what I've already said, I think. So one of the things people do is that they look at the smoothness of the value function. And of course, in order, they're going to find a lot of times that it's not smooth. But if you're lucky and you have a lot of noise in your system, then smoothness is going to happen to your value function, even optimal value function. And in which case, standard approximation theory results would tell you what basis functions to use depending on the degree of smoothness, right? So that's how ideally the analysis goes. Like you look at a system, what properties it has, and then somehow you push things into a smoother space. But there should be life beyond smoother spaces. But it's people are not. I mean, like what is life beyond smoothness spaces? So there could be anisotropic smoothness. So some state variables are more important than others. Most of the variation happens in the direction of some state variables, and the others don't matter at all. Maybe then you can take advantage of this. You can take advantage of symmetries of the problem. So actually, Jude in his presentation is talking about these questions quite a bit. He's an economist, so he cares about certain type of problems. And so he understands in those problems what properties buy you what, and like how you should be setting up your functional approximation in each and every case for those settings. If we think about robotics, you can also see that like problems can be periodic with angles and whatnot, and then maybe basis functions more suited to the periodic case, like sine, cosine. Variations of that wavelets are more suitable, right, than others. So there are these basic things. I don't know of any good book, for example, that would, even though people have studied structural properties of MDPs forever, there is no book that would really go into and describe, the smoothness properties. Actually, the smoothness properties are related to the Navier-Stokes, which is $1 million question. But I mean, like, okay, that's a bit more complicated, but it's a very close related question. If we just stay with smoothness and functional analysis, right? So whether you can have smooth solutions for the Navier-Stokes equation. Okay, so that's my answer. I don't know. Yeah, I guess I mentioned wavelets. Jude mentions that splines are not good. Sometimes these things are a little bit confusing because to me, wavelets and splines are really close. And I think what he means is that splines tend to be defined using tensor product constructions for higher dimensional problems, but I don't think that has to be the case. It is just that, like, very often this is what people do because, I don't know, for historical reasons. And then we see that there are some problems with this approach. In higher dimensional problems, these tensor product constructions need to be avoided. Like, you have to come up with something as.
I kind of have a follow-up to that because we talked about tensor product constructions. Would that be okay?
Yeah, sure.
So definitely, I see why why tensor product constructions wouldn't really be so advisable in higher dimensions. But I know that the idea of tensor decompositions have been around for quite a while. Has there been any work kind of considering that, like kind of assuming like a tensor structure rather than just say m to the p, free entries or something like that?
Yeah, I can't pretend I didn't know the answer or even understand the question. So I understand all the words that you're saying, but I'm not sure that I can make sense of, like, maybe it's a limitation of my imagination of how like tensor product, I don't know, approaches could go beyond this. So you're imagining that there is some big multidimensional tensor, and then there is a low-dimensional factorization of, like a factorized structure on it, and then you just need to discover the structure or something like that, and then maybe
even if it's perhaps assumed a structure beforehand that reduces the number of effective parameters in the tensor.
Right.
Say like a lower rank composition or something like that, for example.
I mean, so what we were writing, you could say that like you can do this individual basis functions and individual variables, and then take the products of those, but limit the order of interaction.
Yeah.
And so if that fits the bill, then sure, like people are doing that in general. But it feels that maybe it's not answering the question in full.
No, that's good to know. I think I would have to kind of compare, you know, maybe it's getting at similar things, but in a different language, you know? So
Yeah. Okay. All right. And you had a follow-up question on Slack as well.
yeah, actually. So the next, I guess my follow-up was more about, say, thinking about, again, continuous state spaces, and how in this lecture we even talked about, say, the allocation problem, where you kind of discretized your state space. In the lecture notes, they talk about, well, you can kind of formulate this as kind of a matrix, or rather your basis is represented as a matrix. Of course, that works. That's kind of equivalent if you're working with a discrete state space. But the continuous state space, estimating, say, that matrix along, say, a discrete grid along your continuous state space, isn't really equivalent to estimating, say, the basis functions or something like that.
So the question is, what happens if you don't have a discrete state space?
It's more like, if you want to assume that smooth, I guess I say this is a follow-up because it's similar to my last question. But if you want that smoothness, then estimating the matrix, or that your basis into the form of the matrix, it doesn't really cut it in terms of smoothness. So I was wondering, how is that addressed? Or
I'm lost a little bit there. What matrix is being estimated? There's no estimation here.
And yeah, so I believe in the lecture notes it said we kind of assume that, or we'll take that, you know, these the basis is given, or these feature vectors are given.
Yeah, okay. So I guess what you're saying is that, okay, let's say we have features associated with just states. Keep it simple. Then there are two views of these things. Like there's a feature vector associated with every state, and you could write down all the corresponding feature vectors and then list all the states. And then, of course, if you have countably infinite or uncountably infinite states, then like what the heck is this? Like, okay, you can write it as a function, right? Like sometimes this is just like, so the reason you write the matrix is because, well, it's the same thing as the function. So it's you don't want to. There is nothing much to be read into that. This has to have two finite dimensions. Like the number of rows in it in this matrix could be as large as you want it. Then it's just viewed as an operator, or it's viewed as the function itself that maps the states to k-dimensional vectors for every state. Because somehow this other, like this row structure is so unimportant. Besides that, there is a certain vector associated with each state. It doesn't matter at all. So you can readily apply everything to continuous state spaces, pretty much. And we are only presenting things for convenience for the finite states case. Yeah, and yeah, so this made me wonder about like why do I write this phi? I like to write this phi because then you can just like write phi theta, and then that's a function from states to reals. And if I have this phi, and phi itself was a function from S to RD, if I write phi maybe transpose theta, or I would write phi theta in a product, then okay, like this could also be viewed as a map from states to the reals, but maybe sometimes it could be a little bit more confusing, but it's really the same thing. I just wanted to avoid confusing people by using this notation instead of this notation. But the extension to the uncountably infinite or infinite state spaces is nothing but just like writing this and then giving a specific meaning to that as a map from states to reals. All right, so this maps to reals, right? Not to RD. Yeah. So there is no estimation. So and we don't need to choose sort of representative states at this stage just to be able to write some matrix, which is a finite matrix. When we do calculations later on, we're gonna be concerned about still how to choose representative states so that if we do calculations at those states, then we have a summary of everything. But it turns out that there the coordinate of the state space doesn't come up, like in terms of that. You can always find a few representative states such that if you're doing calculations at those states, then you're setting up some regression problems. It's like optimal design, optimal experimental design. Then you will find good solutions. So yeah, like that's the beauty of mapping everything to a finite dimensional space. And at one point I said that you want to ask me about whether D has to be finite, because you could also replace this with a Hilbert space, because it turns out that you can do everything that we are doing with Hilbert space valued feature maps, because all that we need to calculate ever with these features are inner products between features and parameter vectors, which also live in this Hilbert space, the same space. So since you can reuse all the calculations because you have squaring everything, so somehow it's very nice algebra. Because of that, you can immediately jump to Hilbert spaces. So you can have, reproducing canal Hilbert space based algorithms. So that's a little step towards having some sort of nonlinearity.
I was actually, just about to ask if there's been any kind of intersection or crossover with reproducing kernel Hilbert spaces, but
yeah.
Sounds like
so this is it. Yeah. Okay.
Hey, thank you.
Thank you for the question. Good questions. All right. Do we have any other questions, like impromptu questions?
I have a small question that I just remembered I had before. I think like 2 lectures ago, you had a little talk about like these global simulators. Then there was like the local simulator, and then there was like the online simulator, where the global one you could just like query any state. The online one you have to query like the one you returned last. So when we do like this planning stuff, like the way we're working with the local planner, we only need to assume an online simulator, right? Or do
It depends. It depends on the algorithm. So some algorithms would want to have a global access. Some algorithms would want to have a local access. Some algorithms are okay with an online access, but not all. Like, so and actually there could be a separation between the harness of the underlying planning problems.
Right. And for the algorithm we talked about for local planning, where we just roll out a bunch of trajectories of size m, I guess there we only needed the online simulator, right?
Did we talk about any algorithm except for today? Oh, it's like the look-ahead tree
Yeah,
thing?
just look at tree stuff.
Yeah. So the look-ahead tree requires online access only. So that's the weakest
Okay.
model.
Right.
That's the broadest model. So
Yeah.
that's great. The next algorithm we're going to talk about is fitted policy iteration. So today I talked about fitted value iteration, right? Essentially. And so in this fitted value iteration, there were these knots where we wanted to calculate values, and they were just taking from the state space like that. So that's global access. That's like magical access to knowing that the state lives in this cube, and I can name any point in the cube and it's a state. That's global access. And we had also access to the underlying values of these polynomial basis functions. So we had global access in this case.
Yeah.
And the algorithm was using global access.
Yeah. And I guess we need it for the approximate policy iteration as well, because we need access to like the subset size d squared of features or feature maps.
So that's coming next time. Yeah, we will have global access there.
Right.
It's very similar to this fitted value iteration stuff.
Okay.
Okay. All right, thank you. Then have a good weekend. It's a little bit further away, but still. See you.